Okay, so hello guys. Let's wait for like 4 or 5 minutes so that a few more can join since there are only two of you in the meet. So yeah, I guess we'll get started in 5 minutes so that a few others can also join. Okay, I guess we can get started since three of you are here and yeah, no one else seems to join. So yeah, I guess we can get started. So just to reintroduce myself. So hello guys, I'm Lakshya Saggi, the TA for the problem solving sessions for this NPTEL. competitive programming course. So I'm the TA for the Tuesday sessions, 6 to 8 p.m. So this week, like previous weeks, also this week, we'll be covering the problems related to week four's content, which was mostly disjoint union sets data structure and its applications. So yeah, the problems which we'll be discussing today will be based on the union disjoint set data structure and yeah, the problems which were discussed in the lectures. So yeah, so we'll be covering problems related to that only. So I guess we can get started. So I'll just share my screen. So if you guys at any point of time have any issues with the screen not showing or font size or my audio is not clearly audible, please inform me via chat. So yeah, I'll try to make it better. So yeah, I guess I'll just share my screen then. So let me just share my screen, guys. And if you have any issues, you can let me know via chat. Okay, so okay, so I hope my screen is visible to everyone and the text is also readable. So if yes, then I guess we can get started. So this week, so again, like previous weeks, since this week we'll be covering like disjoint union set data structure. I'll be assuming that you guys have already seen the lecture videos related to this week's content, and the problems will be built up based on that content only. So I'll be assuming that you have gone through the lecture videos. So yeah, I guess we can get started in that case. So the first five problems are just the problems which are in the ungraded assignments. So you also get the correct answers for ungraded assignments, but I'll still be discussing these problems because you don't get the solutions to these, right? So I'll be covering these problems also so that you can get sort of the solutions for these problems. So yeah. So first five problems which we'll be discussing are the ungraded assignment only. But yeah. So I guess we can get started. So the first problem is consider a situation with three distinct sets, capital X, capital Y, and capital Z, with leaders small x, small y, and small z. So this problem is related to the friendship, the war problem, which was discussed in the lecture videos. So the problem says, so in that, if you remember it correctly, so there were two sets of people, and one set was enemies with the other type of people, and all people of the same type were friends among themselves. So that was the main essence of the problem. So now the problem statement here says that we have three distinct sets, capital X, capital Y, and capital Z, and their leaders are small x, small y, and small z. And it's given to us that small z is enemies with small x and small y. So have all the friendships been accounted for? So the problem statement is essentially saying us that uh, z is just enemies with small x and small y. So, but there's no information given to us about any friendships. We are just given that Z is enemies with X and Y. So, can we still tell whether all the friendships have been accounted for? So, the problem is basically asking so just from this information that Z is enemies with X and Y, can we infer if there is any friendship also in any two sets of people? So, this type of so this problem statement the setting of this problem statement has been covered in the early videos, that just reiterating that there are two types of people. One type is enemies with the other type, and the people of the same type are friends among themselves. So that was a problem statement. I'll be assuming you guys already know about it. So now the problem statement is saying to us that we are given that Z is enemies with X and Y. So can we say that someone is friends with each other also? I believe this is a easy question if you have seen the lecture video. So would anyone like to answer this in chat? So you must have thought about it if you haven't attempted the ungraded assignment also. So would anyone like to not even answer, but just share their thoughts? Maybe what are you thinking? That yes or no? Like, have all the friendships actually been accounted for? So, are there any friendships if Z is enemies with X and Y, or are there no friendships? So yeah. Yeah. So Rasika is typing that X and Y are friends, and Rahul is saying that the answer is maybe no, that there are no friendships. So actually, Rasika, so you are correct. So Rahul, maybe if you have gone through the lecture videos, or I don't know if you have gone or not. So, uh, so what the problem statement actually said was, like I already told you guys, that there are two sets of people, and let's say type 1 and type 2. And type 1 people are all friends among themselves, type 2 people are friends among themselves, but type 1 and type 2 people are enemies with each other. So from this, what can we say is something like this, that Z is enemies with X and Y. So suppose Z was type 1, then X and Y both are type 2, right? Because there are just two types of people, and Z is enemies with X and Y. So these two will be type 2, and since X and Y both are type 2, and people of the same type are friends among themselves, so X and Y will actually be friends with each other. And that is the only case when they will be mutual enemies of Z. So yeah. So actually the answer is uh, hmm, small x and small y will also be friends. And why is this the case? So this type 1 and you can give the type 1 and type 2 reasoning, or you can also say using the indirect comparisons which was discussed in the lecture. So they are essentially the same thing, the argument which I'm giving and the argument which I'm going to write. But yeah, so this is because mm, two people having, so maybe two, I'll write X and Y in parentheses. So the two people are here. So two people having a common enemy are friends. So having a common enemy. So who are the two people? So two people are X and Y, and who's the common enemy? So common enemy is Z. So are friends with each other. So yeah. So any two people, so the two people here are X and Y. If they have a common enemy, the enemy here is Z, then those two people are actually friends with each other. So yeah. So this is actually the correct answer. So it's a straightforward question. So, but still, this question, like these sort of question are there to give you a feel of what the problem statement actually was saying. So yeah. So now the second problem says that, so again, if there are any, so first of all, like if there are any doubts or anything, you can inform me via chat. Just reminding you guys. So feel free to ask questions in chat. So yeah. So the second problem says that suppose X and Y are enemies and we are asked to make enemies between small a and small b, where A belongs to the same set as X and B belongs to the same set as Y. So belongs to the same set actually means that they are actually friends with each other. So yeah. So the problem statement actually says that uh, we know already that X and Y are enemies. And we also know that A belongs to the same set as X, which means that A is a friend of X and B is a friend of Y. And now a query comes which asks us to make enemies between A and B. So now the problem is asking us, is this query even possible? Like, if we are asked to make enemies between A and B, can we actually make those enemies? Is this a contradiction or not? So again, I think this is a, yeah. So Rahul is saying that no contradiction is possible. So yeah, Rahul. So actually, your answer is correct. So yeah, so there is no contradiction. And why is this the case? So you can just see it via type 1 and type 2. which I was saying earlier. So suppose X and A are of type 1 and Y comma B. So maybe suppose X comma A are of type 1 and Y comma B are of type 2. Then you can actually see that all conditions are satisfied. So then it is easy to see that all conditions are satisfied. And why is this the case? So X and A are of type 1 and Y and B are of type 2. This means that X and Y will be enemies since they are of different type. And A and B will also be enemies because they are of different types. And A and X will be of the same type, so they are friends. Similarly, B and Y will be friends as they will be of the same type. So yeah. So so there is no contradiction in this second problem. So yeah, good job, Rahul. So then maybe we can come to the third question then. Okay, so this question is related to complexity of the disjoint set union data structure. So the problem asks us that suppose you have a DSU data structure. DSU is just the disjoint set union data structure that has already been created. And there are a total of n vertices in the entire data structure. So a disjoint set union data structure has already been created for us, and we are given that there are a total of n vertices in the data structure. And now the problem asks us that we have to process m queries of the find type and no query of the union type. So what is the worst case time complexity for this without path compression? So So let's just highlight the main, first of all, main things which the problem is asking. So we are given this DSU data structure, which has n vertices. And now we have to process m queries of the find type and none of the union. So all queries are of the find type. And so find query just asks us to find the set to which, maybe to find the leader of the set or something like that, right? And no queries of the union type. And now the problem asks us what is the worst case time complexity for this without path compression. So note that with path compression and without path compression, the query time can change, as was discussed in the lectures also, that path compression actually helps us in reducing the time complexity. But that's a story for another day for other questions. But yeah. So the problem basically asks us that no union type query is asked, only find type query is asked, and there are m such queries. And now what is the worst case time complexity for this? Okay, so Rahul is saying that the answer for this should be order m. So, and Vishal is saying that the answer should be order mn. So, okay, so guys, can you also type some of the reasoning? Like, why did you arrive at these answers? Maybe like, why do you think, Rahul, that the answer should be order m, and why would be m and Vishal? Okay, so we have another type of answer. Rasika is saying actually the answer should be m log n. So we have three possible answers: order m, order mn, and order m log n. So you guys can also type in chat your reasoning of why did you arrive at this answer. Till then, I can actually tell you guys that actually, yeah, Rasika is correct that the answer will be actually m log n. So the worst case time complexity will be something like order m log n. And why is this the case? This is because actually this DSU data structure, it is given to us that uh, we are not using path compression. So if we are not using path compression, then every query takes order log n time, if you guys remember. So there are total n vertices in the entire data structure. And remember that we talked in the lectures that the tree in the disjoint set union data structure will have a maximum height of order log n, the tree which we make. So traversing any path from any child to any root will take something like an order log n time. So in the worst case, a query can take order log n time. And since there is no path compression, so there will be no restructuring also. So because of this, what happens is each of these queries can take something like a login time. So there are m queries and there is no union type query. So each of these m queries actually can take something like a login time. So in total, these m queries will take m login time. Yeah, yes, Rahul. So actually Rasika is asking in the chat whether depth of the tree is login. So yeah, Rasika. So I think there was a bit of a confusion in the solutions given to this problem because the answer was given as mn as well as m login. But I believe that m login is the correct answer because whenever we are talking about the DSU data structure itself, then we are already assuming that the data structure has been made in an efficient manner, right? So whenever we create a data structure, we create it in an efficient manner. And the efficient manner in this DSU data structure is to create trees with a maximum of log n height. So if there are n vertices, then at any point of time in DSU data structure, the height will maximum be log n. So that's why you can assume that the height of the tree will be log n. So yeah, I believe this can be a bit confusing that we are just given n vertices and we don't know whether the height of the tree is log n or n. But we sort of already know, right, that whenever we are talking about DSU data structure, we'll be talking about trees with height log n. So yeah. So Rahul is saying that he also got why the answer is m log n. So yeah. So this is because there is no path compression. So note that since there was no path compression, each query can take same amount of time. There will be no restructuring, no path compression. Uh, each query can take order log n time, and as there are n queries, total time taken is order m log n. So yeah. So yeah, I hope it's clear to everyone why is this the case. So then we can move on to the next question. So yeah, so it's again a variant of the third question only, but now the DSU has already been created. There are a total of n vertices, and now we have to process m queries of the find type and none of union. Again, we have to only process queries of the find type and none of union. But the problem is asking us that we have to do this now using path compression, not without. So in the first problem, we were not using path compression. In this problem, we are actually supposed to use path compression. Then what will be the worst case time complexity here, according to you guys? So, so note that we have to process m queries, and this time we are allowed actually path compression, and all the queries are of the find type actually. So, guys, would anyone like to answer this in chat? Okay. So yeah, so actually Rahul is saying that the answer would be order M, and he's asking us what actually amortize means. So sure, Rahul, I'll come to your statement also, but let me just write down the answer first. So yeah, actually Rasika is also saying that the answer would be order M. So yeah, good job, guys. So this is the correct answer. So the answer will be order M, amortized time. Or maybe so in the options for this there was an option of order m plus n, so that is also correct because generally the number of vertices is smaller than the number of queries which we make. So you can write this as order m, or some people also like to write it as order m plus n. Doesn't matter much because both is linear. So yeah, so you can write anything order m, or so both types of answers can be correct. It doesn't make much of a difference. So this is because uh, we are using path compression, and each query takes order 1 amortized time if we use path compression. So yeah. So this is the answer, that the answer is something like order m, or we can just say order m plus n, doesn't matter much. But note that this is actually amortized time. So like, so Rahul is asking us that what does actually amortize mean, right? So Rahul, for answering your question, maybe what I can do is maybe I can give you a high level idea first. So what amortized time actually means is that uh, suppose I give you a task. Suppose I tell you to do some task for the first time. So what happens is generally suppose you're doing something for the first time. Suppose suppose you're writing your name for the first time, or let's say you're putting down your sign for the first time. So whenever you're putting down your signature for the first time, you'll take a little more time, right? For writing down your name, or let's say signature. Or let's just say like writing down your name, you'll take more time. Let's say you'll take 5 seconds for writing your name, Rahul, when you're typing it for the first time. Maybe after first time, you will take a little less time because you will get accustomed to writing your name. So let's say after writing your name, let's say on 100 different instances, you will take, let's say, 2 or 3 seconds only instead of 5 seconds for writing out your name, Rahul. Right? For spelling out your name, you will take like less time, like you'll take like 2 seconds or 3 seconds instead of 5 seconds, which you took the first time. So when someone asks you how much time do you take to write your name, and you have already written your name, let's say in the past for 100 times. So what you'll actually be doing is you won't be saying that I take 5 seconds to write my name, because that was just the first time when you took it. But you also won't be saying that you take 2 seconds to write your name because you took 2 seconds to write your name after the 100th time. So what you will be doing is you will be taking a good measure would be to take the average of the first 100 times, right? For first time you took 5 seconds, for second time maybe you took 4 seconds, for third time again 4 seconds, and so on. So maybe for all these times you can take an average. And let's say the average comes out to something like 3. So it means that Rahul takes approximately 3 seconds to write his name, amortized time. So amortized is nothing but you can say the average time taken. So do you get the drift of it? What I mean you say? So what this actually means is, so I can remove maybe amortized time here. So this order one amortized time query time, what actually this means is that each query may not take order one time exactly. So what may happen is first query may take, let's say, m time. So let's just take an example here only. So explaining a bit of explanation for amortized time. Explaining amortized time. So suppose first time the query takes. So suppose the first query takes maybe. So suppose the first query takes order m time. So the first query which we are doing, let's say it takes order m time and not actually order one time. But let's say but what happens is after doing this first query, the future queries actually become faster. So path compression actually does this for us, right? Using path compression, the first query may take more time, but future queries become cheaper for us. So what happens is the first query takes order m time, but let's say the next m minus 1 queries take order one time each. So note that worst case time complexity for a query is still order m, because one query can still take order m time. But what we are saying is first query is taking only order n time, but next m minus 1 queries take order one time each. So all other queries are faster. One query is just very expensive for us. So saying that the time is actually order m will be bad for us because it's just one time instance and other times actually it's just order one. But saying it directly as order one will also be wrong because there is one instance where it takes order m time. So that's where amortization comes into picture. So what we actually report is the average query time. So we have these m queries. One query is taking order m time. Next m minus one queries are taking order one time each. So average query time will be something like so. I hope everyone knows how to take average. So there are m queries. So first query is actually taking something like an order m time. So maybe instead of writing this as order m, I'll just replace this by n because it does not matter much. And there are the next m minus one queries, which take something like one time. And now we are taking the average over m queries. So we'll divide it something by m. So I hope you get how I got this average query time formula because there was one query which took m time, then the remaining m minus one queries took one time each, and we are taking average over the m queries actually. So yeah. And this is what the average query time will look like actually. So this will be something like m plus m minus 1 divided by m. So it will be approximately equal to 2, right? So what we actually arrive at is the average query time will actually be a constant only. Even though once we took order m time, the average query time over m queries takes only a constant amount of time. So it does not take actually this time, the one time, but the time just doubles to 2, but it's still a constant. So amortized time is a constant in this case. So is a constant, or we can just say something like an order one. So okay, Rahul, so Rahul is asking chat the first query is order M or order N. So let's say so I was just giving this example of uh, I was just giving this example for general general explanation of amortized time. So let's say we are not talking about this problem, but in general, let's say we are talking about this that we are given m queries and first query takes order m time and next m minus one take order one time. So yeah, in this problem, in this fourth problem, it will be something like the first query takes log n time. So maybe if we are using this sort of example, something what I can actually give is let's say the first m by log n queries take log n time each, but next remaining queries take only order one time or something like that. So this example is actually not related to this problem, but just a general explanation of why do we need the notion of amortized time and what actually does it mean. So this is not actually related to this answer. Uh, what I'm saying is maybe I should replace the symbol. Suppose we have q queries for a problem. Suppose the first query takes order q time and the remaining q minus one queries takes. So average time is because I believe the M and the M symbol can be a bit confusing because it was used in the problem also. So yeah. So let's say I'm giving a general. So yeah, so Rahul, I understand what you're asking. So you're saying there are n vertices and m queries. So what I'm saying is this notion of amortized time is independent of this. So the n vertices and the m queries are for this specific DSU data structure, right? But this notion of amortized time is independent of this data structure. Like E, so I'm explaining the general concept of amortized time. What does it mean? So here definitely, so for this DSU data structure, actually, so the first query time will be something like a order log n only. So maybe like suppose there was some condition that first query time was just log n and remaining was order one. Then maybe we could have obtained some other amortized time, but what I'm saying is let's just keep this separate from this amortized time notion. Maybe I can put it at the top that this is not related to any problem specifically, but just uh, but just something which I am explaining independently of the problems. So okay, so I hope you understood a little bit more about it. So it's uh nothing too fancy, the notion of amortized time, Rahul. What it just says is that some query can take larger time, some query can take lesser time. So we just take the average over all the queries. So that's what we are doing here. The first query takes order q time, next q minus one query take order one time each. So the average actually comes out to a constant only. And that is what we call amortized time. So here actually you can prove that whenever you process any m queries, so I'll not be proving this, but you can read about it yourself, that in the DSU data structure with path compression, if you process m queries of the find type, then these m queries together will take maximum order m time. So m queries together will take maximum of order m time. We are not saying individual query, how much time will individual query take, but m queries collectively will not take more than order m time. And the total time taken, the average times will be just total time taken divided by the number of queries. So if total time taken is something like an order m and the number of queries was also m, so m by m will give us something like an order one amortized time. So you can read more about it yourself, but this is the high level idea for amortized time. Just take the total time taken over all the queries and divide it by the number of queries. So yeah. So if there are still some doubts, maybe you can ask me in chat. Uh, Till then, I can move on to the next question. So this is also a bit straightforward question only. So suppose you have a disjoint set union data structure which consists of trees T1 and T2, and the depths of these trees are K1 and K2 respectively. And now we want to perform a union operation between vertices V1 at depth D1 from T1. So V1 vertex is in tree T1 and V2 is in tree T2. And now we are performing a union operation between these two vertices. So what will be the depth of the newly formed tree? Maybe I can just write it as what is the depth of the newly formed tree? And we are given that K1 is actually less than K2. So we are given actually two trees, T1 and T2. One has depth K1, other has depth K2. And we know that K1 is less than K2. And now we are actually merging those trees using union operation. So now we are asked what is the depth of the tree after the union operation. I believe this is also a straightforward question. So yeah, so Rahul is typing in chat that the answer should be K2. So yeah, Rahul, actually you are correct that the answer is K2. And why is this the case? So this is because uh, K1 is the smaller height tree. This is because T1 gets attached to the root of T2. And this is because height of T1 is less than height of T2. Or maybe depth is a better word. Depth of T1 is less than depth of T2. So what actually happens is since this K1 was actually less than K2, so the height of T1 actually the leaf vertex, so the child vertices of T1 have now the path from child the leaf vertices of T1 to the root actually increases by 1. The path length of the root, the leaf vertices of T1 to the root of the tree increases by 1, because all of these now, because T1 is now getting attached to root of T2. But so what actually happens is the depth of the vertices of T1 actually increases by 1. So if there was a vertex of depth 4, now that vertex will have a depth of 5. So if there was a vertex of T1 which had a depth of 4 earlier, after the union operation it will have a depth of 5. But note that the highest depth which a vertex could have had in T1 earlier was K1. So now the depth of that vertex will actually become K1 plus 1 only. It can't be more than K1 plus 1. But we already know that K1 was less than K2. So K1 plus 1 will be just less than equal to K2. So the depth will still be K2 only. I hope you get the high level idea, but maybe I can just write it down also. So depth of vertices of T1 increases by 1. The max depth of T1 is now K1 plus 1. So earlier the max depth for a vertex of T1 was K1, but now it becomes K1 plus 1. So, but we know that K1 is actually, so we know that K1 is actually less than K2. So this implies that since K1, K2 all are integers, so actually this implies that K1 plus 1 will also be nothing but less than equal to K2. So we can see that the depth of all vertices of T1 is bounded by K2 only, and depth of all vertices of T2 was already bounded by K2. Hence, depth of all vertices of T1 and T2 is less than equal to K2. So depth of the newly formed tree is equal to K2. So this is a straightforward question, but I believe the argument when you write it down becomes a bit yeah, it involves a lot of words, but yeah, you can see it via figure easily that the answer should be K2 only. And this is because depth of all vertices of T1 and T2 is now less than equal to K2. So depth of the newly formed tree will be nothing but K2 itself. So one thing which I want to point out in this problem is that note that the final depth of the tree does not depend on the depth of the vertices of whom we are taking the union. So in the problem we are also given that we are taking the union between vertices V1, which is at depth D1, and vertex V2, which was at depth D2. But note that these D1 and D2 do not come into play in the final depth of the newly formed tree. So just keep in mind this that the depth of the final tree form won't depend on the vertices, because in the end we are just making one tree attached to root of the other of another tree. So these depths of individual vertices won't matter. Maybe I should put this down as a note also, but even though it's straightforward, but still, I believe easy to see that the depth of the newly formed tree does not depend on the depth of the vertices whose union we are taking. So the depth of the vertices whose union we are taking, so depth was D1 and D2, but these D1 and D2 do not come into the picture for the depth of the newly formed tree. It is just equal to K2. I hope you guys understand what I was trying to say here. And just a side note, so suppose K1 was actually equal to K2. suppose K1 was not strictly less than K2, but K1 was actually equal to K2, then what will be the depth of the newly formed tree? So, so yeah. So Rasika is answering in chat that the answer should be K2 plus 1. So yeah, so this is easy to see because the depth of all the vertices of, so any of the tree can get attached to any other and it won't matter, and depth of all the vertices of that tree will increase by 1. So the answer will be K1 plus 1 or K2 plus 1. You can just say anything as K1 is equal to K2. Also, if K1 equal to K2, then depth of the newly formed tree is nothing but K2 plus 1. So yeah. So yeah, just pointing it out, although it's easy to see, but still. So, okay then. So maybe then if there are any doubts, you can ask me in chat. Otherwise, I'll just move on to the sixth question now. Okay, so sixth question is a similar question to sixth question is also in this week's assignment. So, and this question is not quite related to the problem which have been discussed in the lectures, but yeah, it's something similar. So you can see this. So just pay attention to this, guys. So the problem is asking us that in a social network, people are connected by friendships. So this is given to us and given a list of friendships, determine the number of friend circles in the network. And how do we define a friend circle? A friend circle is a group of people who are directly or indirectly connected by friendships. So let's say I am friends with some person. So let's say there are persons A, B, and C. Suppose A is a friend with B and B is a friend with C. So even though A and C are not actually friends with each other, just A is a friend with B and B is a friend with C, we will say that A, B, and C are all in the same friendship circle. So this is what the statement actually says, that a friend circle is a group of people who are directly or indirectly connected by friendships. So A and C are actually indirectly connected by friendships in the sense that A and B are connected by a friendship and B and C are connected by a friendship. So that's why A and C will also be connected by a friendship. So this is the definition of a friend circle given to us. And now we are given 11 people labeled 0 to 10 and following pairs of friends. And now we need to find out how many friend circles are there. So this problem actually involves a bit of diagrams based approach. So I have a diagram also, which I'll be sharing with you guys. So we'll be doing this using bit of diagrams. So, but just get these definitions in mind that the number of friend circles, we need to find the number of friend circles, and a friend circle is nothing but a group of people who are directly or indirectly connected by friendships. So note that um, So note that if I hope this diagram is visible to everyone clearly. So what I'm trying to say, suppose 0 and 1 are friends, and similarly 1 and 2 are friends. Let's just put an edge. Suppose if 0 and 1 are friends, let's just put an edge between them. Similarly, let's put an edge between 1 and 2 if they are friends. So if this is the case, then what I'm saying is 0 and 2 will also be friends, because 0 and because 0 and 2 are indirectly connected by friendship. So 0, 1, and 2 here are in the same friendship circle. And similarly, 3 is in its own friendship circle here, 8 is in its own, 7 is in its own friendship circle, and so on. So actually, if we make a diagrammatic representation for the problem and we have an edge for every pair of friends given to us, then we just need to find out the number of connected components in the graph. So like in this example, this is one connected component, this 0, 1, 2, and this is a friendship circle. Similarly, 10 is in its connected components of its own. So this is in it one friendship circle. Similarly, 9 is in its own friendship circle, and so on. So diagrammatic, if we reduce this problem to a diagrammatic graph representation, then what the problem is asking us is that just create a vertex for every person and just add an edge for every friendship which is given to us. And finally, just output the number of connected components of the graph. And I am assuming like you guys already know what a connected component is because something like this was also covered in the lectures. But yeah. So I hope everyone gets the gist of it. If there are still some doubts about what the problem is asking, please ask via chat because a similar problem is present in the this week's assignment also. Okay, so I'm assuming everyone understands what the problem is essentially asking us. So what we are supposed to do is essentially treat all of these pairs of friendships. So 0 and 1 are friends. So we can insert an edge in the graph for this. Similarly, 1 and 3 are friends. So we can insert an edge for this also. So we'll be adding all of these friendships as edges. And in the final resulting graph, we'll just have put the number of connected components. And that will be the answer for the number of friend circle. So maybe we can get going then. Okay, so yeah. So initially, let's suppose no friendship was given to us, then this was the graph. So everyone was alone. But now we are given that 0 and 1 are friends. So we can introduce an edge between 0 and 1 to say that they are actually friends. Similarly, it's given to us that 1 and 3 are friends and 0 and 3 are also friends. So I'll be adding an edge between 1 and 3 because 1 and 3 are friends. And I'll also be adding an edge between 0 and 3 because it's also given to us that they are friends, right? After this, we are also given that 5 and 8 are friends. So I'll be adding an edge between 5 and 8. So 5 is here. And for a bit more clarity, I'll be just moving 8 here. And yeah. So now we have that 5 and 8 are friends. And it's also given to us that 6 and 10 are friends. So 6 is here, 10 is here. I'll be moving 6 a bit here for clarity. So I hope everyone understands the procedure which I'm employing. If there is any doubt, you can ask me via chat. Just reminding you guys. So 6 and 10 were friends. Now 7 and 1 are friends and 7 and 0 are friends. So 7 is friends with 1 as well as 0. So I'll be adding an edge between 7 and 1. I'll also be adding an edge between 7 and 0. And now the 7 and 3 are friends and 9 and 4 are friends. So 7 and 3 are also friends. So 7 and 3 are actually friends and 9 and 4 were friends, right? So 9 is friends with 4. So after this, it's also given to us that 9 and 2 are friends. So if 9 and 2 are friends, then 9 here and 2 is here. So 9 and 2 are also friends. And final two pairs are 4, 2 and 6, 4. So 4, 2 and 6, 4. So 4 is friend with 2 as well as 6. So 4, 2 and 6, 4. Okay, so 6 is here and 4 is here. So something like this. Maybe I can write this. So yeah. So this is actually the graph which is given to us. This is the friendship graph. So just to verify that we have made this correctly, we can just count that the number of edges should be equal to number of edges in this graph should be equal to the number of friendships which were given to us in the list. So let's just count the number of edges. So this is 1, 2, 3, 4 edges, 5 edges here, 6, 7, 8, 9, 10. So there are 11 edges in this graph. And let's just see how many friendships were given to us. So 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there were 12 friendships, but how many edges? Okay, I counted. So there are these 6 edges here. So there must be 12 edges present here because we are given 12 friendships. So there are 6 edges in this part there are 5 edges in this part, so 6 and 5 becomes 11, and one edge here. So there are 12 edges present for 12 friendships. So I guess the diagram will most probably be correct. And now, can anyone answer how many friend circles will be there using this diagram? So, so yeah. So Rahul is typing in chat that there will be 3 friend circles. Okay, so Rasika is saying that there will be 7 friend circles. So why do you think there will be 7 friend circles, Rasika? Ah, so note that what I told was that the number of friend circles will be nothing but the number of connected components in the graph. So here actually there are just 3 connected components, right? Because 5 and 8 form a component on its own. Similarly, the vertices 6, 10, 2, 9, and 4 form a connected component of their own. And similarly, 1, 3, 0, and 7 form a connected component of their own. And these components don't have any edge between each other. So they are just 3 connected components. This one, and this one. So there should be 3. Okay. So Rasika saying she got it. So yeah, that's why there will be 3 connected components. Good job, Rahul. So yeah, there will be 3 friend circles. And what will the friend circles look like? We should tell that also, just for better understanding. So circle 1 will be consisting. So let's say this is the first circle. So this will consist of people 0, 1, 3, and 7. 0, 1, 3, and 7. Similarly, circle 2 will be consisting of 2, 4, 6, 9, 10. 2, 4, 6, 9, 10. Right. And so maybe I can note it in Romans because it can get a bit confusing. So the circle 3 will be just 5 and 8. So this is the first friend circle, this is the second friend circle, this is the third friend circle. So there are 3 friend circles in the network, and these are the 3 network. These are the 3 circles. So yeah. So the correct answer is actually 3. Just underline this in case. So I hope everyone understands this problem, and if there's any doubt, you can ask me because as I said, there's a similar problem in this week's assignment also. So yeah. Otherwise, I can just maybe move on to the next question now. Okay, so 7th question actually says that consider the following pseudocode for find set and union set operation for disjoint set union data structure. So these find sets and union sets, we already know what they do. So union set operation just takes union of 2 sets. Find set just tells us the set to which an element belongs or something like that. So yeah. So now here is the implementation for these 2 functions given to us. So this is a piece of code, a piece of pseudocode where the implementation is given. So parent, so we are given a array. In the first line, we are given a parent array. And also the find set function is defined as something like if parent of u is set to u, then actually return u. So what this means is that or otherwise what we are doing is we are returning the find set of parent of u. So if you guys remember, this is nothing but this is nothing but just the algorithm of moving the pointer towards parents till we reach the root of the tree. So this is nothing but that only. So this was covered in the implementation part already. That yeah, that we are just moving on to the parents of. So if we want to find out the set of a node u, so we just move on to parents of u's till we arrive at the root or the special node or the leader, which we say. the property of the leader is that the parent of the leader is nothing but the leader itself. So yeah. So find set function is doing something like this. So note that the find set in this context, in this problem, is not using path compression because we are not changing the parents as we move along. So here find set is not using any path compression. And the union set operation is just doing u is fine. So we just find the leader, or let's say the find the set of u and we find the set of v. And if u and v are different, so what this means is that leaders of u and v are actually different, then we just set parent of v to u or something like that. So note that here also in this union set operation, we are not doing any rank comparisons or anything. Like in this union set problem, we are in this union set function, which has been defined for this seventh problem, we are just taking u and v and we are just setting parent of v as u. We are not comparing the depth of the two trees and then assigning u to the and then assigning root to the higher depth tree or anything like that. So we are just arbitrarily doing that parent of v is u. So I believe these two functions are clear to everyone. And then the problem actually is asking us that we are given an array parent. So we are given this array. We are given a parent array representing the parent array of the disjoint set union data structure for 6 vertices labeled from 0 to 5. So we have 6 vertices labeled from 0 to 5, and we are given a parent array. And now after performing a series of union operations, so let's say we have already performed some union operations using the provided pseudocode, the pseudocode provided above, the parent array actually becomes something like this. So what happens is the parent array becomes something like this 0, 2, 2, 1, 4, 5. And now the problem is asking us what will be the result of the operation find set of 3. So the problem is just asking us that we are given the parent array to be, let's say, something like this 0, 2, 2, 1, 4, 5. And now we want to find out what will be the result of find set of 3. If I invoke the function find set on input 3, what will be the output if the parent array is something like this? So again, I believe this is a simple question. So what we just need to do is we just need to simulate this find set function on this parent input. Or you can just do this like yeah, you just have to run this find set function on this input. Or if we already know we already know from the lectures that what the find set function does, it just moves on to the it just moves on to parent of every node till we arrive at a leader, right? And leader is recognized by saying that a vertex is a leader if parent of that vertex is actually equal to that vertex itself. So something like this. So let's just see what will happen in this case. So we are given that we need to find set of 3. So the input here is find set of 3. And now we see what's the value of parent of 3. So what's the value of parent of 3 in this array, guys? From this array, what is actually parent of 3? Can someone answer in chat? Okay. So Rahul is saying 1. So yeah, good job, Rahul. So note that there are 0 index vertices. So parent of 3 will be nothing but this will be parent of 0, this will be parent of 1, this will be parent of 2, and this will be the parent of 3. So 1 is actually parent of 3. So, so parent of 3 is actually equal to 1. So what happens is now we move on to, so what happens is now we arrive at the vertex 1. And now we want to find out whether 1 is a leader or anything or something like that. So first we need to find out what's the parent of 1. So again, now what will be the parent of 1 in this array? So while moving from 3, we just move to parent of 3, which was 1. And now we'll try to move to parent of 1. So what will be the parent of 1 here? Okay, so good job, Rahul. So Rahul is saying that parent of 1 is true. So you can see that parent, this is 0, this is first index. So parent of 1 is actually 2. So parent of 1 now becomes actually 2. And now again, it can be seen what's now we'll just find parent of 2 now. And what will the parent of 2 here? So this is 0, this is 1, this is 2. So parent of 2 is actually 2 itself. Parent of 2 is actually 2 itself. So what does this mean? This means that 2 is the leader of the set. So 2 was the leader. So what actually happens is if parent of 2 is actually equal to 2, then we are actually returning u. So we'll be actually returning the value 2. So so the problem asks us what will be the result of the operation find set of 3. So the result of this operation will be nothing but 2, because we finally arrived at a vertex 2, which was the leader of the set to which 3 belong. So first we move. So just to reiterate, what we did was we started out with 3. Then we found out the parent of 3, which was 1. Then we found out parent of 1, which was 2. And then we found out parent of 2, and it was 2 itself. So because of this, we could say that 2 is actually the leader of the set to which 3 belong. So that's why to which 3 belong. So that's why the find set of 3 will just return the value 2. So find set of 3 is nothing but 2. So the correct answer for this will be 2. The value of find set of 3 will be equal to 2. So is this clear to everyone? If it is not clear, I can ask me in chat. This is just simulating the find set algorithm, which has been whose pseudocode has been provided here and which has been discussed in the lectures also. So yeah. So after this, maybe we can come to the eighth problem now. Okay. Maybe I can put this next page. Okay. So eighth problem is asking us consider the following updated pseudocode. So in the seventh problem also we were provided some pseudocode for disjoint set union data structure. But now let's say we update the pseudocode for find set, and now we are using, let's say, path compression also. So in the seventh problem, recall that we did not use path compression, but let's say now we update the pseudocode such that the code now uses path compression. So in the eighth problem, let's say we are given this parent array, and in the find set operation, uh, we are also changing the value of parent of u if u is not the leader, and we change its value to find set of parent of u. So this is what path compression does, if you guys remember, right? So now in this eighth problem, actually in the find set operation, we are also using path compression. And now suppose for an instance, parent array looks for so let's say we are given 8 vertices from 1 to 8 here. Not from 0 index, but let's say we are given 8 vertices from 1 to 8 here. And parent array looks something like this, that parent of 1 is actually equal to 1, parent of 2 is 3, parent of 3 is 1, parent of 4 is 2, parent of 5 is 3, and so on. And now we need to answer what would be the state of the parent array after the following operations are performed in this order. Suppose we first perform the operation find set of 7, and then we perform the operation find set of 8. And after this, we need to find out what would be the final value of the parent array. So note that this parent array can change from the initial value of the parent array. And this is because we are actually using path compression in the find set. And when we use path compression, uh, we actually also change the parents of the vertices along the way. So I hope everyone understands the question at least. So we are given the initial parent array, and we are given that we are using path compression. And now after find set of 7 and find set of 8, these two commands, these two queries in the given order, what we need to find out what will be the value of the parent array. And we are given 4 options. And I don't think 4 options matter, but yeah, just for ease, we are given 4 options and we have to select one of those. Okay, so maybe we can get started. So yeah. So initially what the parent array looked like was, so maybe I'll just, for ease, I'll just denote the parent array using an array only. And I'll assume that we are using one indexing. So the initial array will be something like 131, 23344. 1, 3, 1, 2, 3, 3, 4. So note that we write down. So this parent is so what does this 1312334 mean? That parent of 1 is actually 1, parent of 2 is 3, parent of 3 is 1, parent of 4 is 2, parent of 5 is 3, and so on. And you can just see that this is actually the initial array given to us. The initial array, parent of 1 was 1, parent of 2 was 3, parent of 3 was 1. So 1312334 actually denotes the values of the parents. And we are assuming from what is our live index from 1 to 8. And now from the initial parent array we are given, first we invoke the find set of 7. So what does find set of 7 do? So what happens when we use the function find set of 7? So first we find out the parent of 7. Like you don't even need to look at the code itself because we know what the path compression does and stuff like that. So we can just do it ourselves also. So for using find set of 7, we first find the parent of 7. So what will be the parent of 7 here, guys? Okay, so Rahul has already arrived at the at the answer and he's saying that option 4 is correct. But maybe Rahul, maybe option 4 is correct or not, we'll just see through it. Maybe we can go through step by step so that it's easier for everyone. So we are invoking find set of 7 initially. So first we'll need to find out what's the parent of 7. So in this array, according to you guys, what will be the parent of 7, guys? Okay, so Rahul is saying that parent of 7 will be 4. So parent of 7 will be, so note that we are using one based indexing. So this will be parent of 1, this will be parent of 2, parent of 3, parent of 4, parent of 5, parent of 6, and parent of 7. So parent of 7 will be nothing but 4, right? So from this, we'll need to move on to parent of 4. And now parent of 4 will be something like parent of 1, parent of 2, parent of 3, parent of 4. So parent of 4 will be 2. And now we'll move on to parent of 2. And parent of 2 will be 0, 1, and 2. So it will be 3. And now parent of 3 will be 1, 2, and 3. So parent of 3 will be nothing but 1. And now what will the parent of 1? It can be seen that parent of 1 will be nothing but 1 itself. So I hope everyone is able to follow along. We are just following the chain of parents to find the leader. And now we have found out that the leader is actually 1. So find set of 7 will actually return that the leader is 1. But along the way, it will also change the values of the parents for these nodes. So we know that all of these nodes have 1 as the leader, right? All of these nodes in the chain have 1 as the leader. So we can just directly set parent of 4 to 1, parent of 2 to 1, and parent of 3 to 1. So what happens is, so find set of 7 is 1, and as we are using path compression, the parents of all vertices encountered along the path also changes to 1. So what actually happens is we change the parents of vertices which we encounter in the path. So initially the path started at 7, then it moved to 4, then it moved to 3, 2, it moved to 3, and then 1. So we change the parent of 7 to 1, parent of 4 to 1, parent of 2 to 1, and parent of 3 to 1. Parent of 1 was already 1, so we don't need to change it. So what happens is parent of 7 actually becomes 1. So we change. Okay, maybe I should write. So we make the following changes in the parent array. And what are the changes which we make? The changes which we make are we make parent of 7 as 1. We also make parent of 4 as 1 because 4 was also encountered in the path. Then 3 was also encountered. So we change the parent of 3 also to 1. And yeah, other parents remain the same. So from this array, so the value of this array changes. And now the value of array actually becomes something like this. Maybe I should write it. Okay, so parent. So after first query, parent actually becomes, so this was the initial parent array, and the changes made to this array is we have made parent of 7 to 1, we have made parent of 2 to 1 also. I think I missed it. We have set parent of 4 to 1, we have set parent of 2 to 1, and we have set parent of 3 to 1. Yeah, Rahul also pointed out in chat that we make parent of 2 is equal to 1 also. So now in this parent array, we make the changes that we made parent of 7 to 1. So 1, 2, 3, 4, 5, 6, 7. So we make parent of 7 as 1. We also make parent of 4 as 1. So 1, 2, 3, 4. This is also set to 1. Similarly, parent of 2 is set to 1. So 1, 2. This is also 1. And parent of 3 is also 1. So 1, 2, 3. Okay. Yeah. Okay. So parent of 3 was already set to 1. So we don't need to make the any changes. But yeah. So this becomes the parent array after first query. And now we invoke the second query. And we, in the second query, this will be the parent array which will be used. Second query was first we invoke find set of 7, and now we invoke find set of 8 now. Right. So now we invoke something like a find set of 8. And what happens on invoking find set of 8? So we first find the parent of 8. So parent of 8 is easy to see again. 1, 2, 3, 4, 5, 6, 7, 8. So parent of 8 is nothing but a 4. And now we move on to 4 and find out the parent of 4. So parent of 4 will be nothing but 1, 2, 3, 4. So it will be 1 again. So parent of 4 will also be 1. And we know that parent of 1 is 1. Yeah. So what happens is maybe I should just copy paste this text and yeah. So we find out that parent of 8 is also in fact 1. So find set of 8 is also 1. And as we are using path compression, parents of all vertices encountered along the path also changes to 1. So what we do is we make the, so I'm just copying this text, but yeah, I'll be changing the values. So we make the following changes in the parent array. And what changes are we making? So first vertex which we encountered in the path was 8. So we changed the parent of 8 to 1. Second vertex was 4, and its parent of 4 was already set to 1, so we don't need to do anything. So yeah. So only these are the changes which you need to make, and yeah. So after the second query, the parent array is actually equal to. So after second query, sorry, parent array actually becomes. So this was the array after the first query, right? And now in this array, we have made the change that parent of 8 is 1. So 1, 2, 3, 4, 5, 6, 7, 8. So we may change the parent of 8 to 1 and parent of 4 is already 1. So this is the array which we arrive at after the second query. Second query. So I believe this will be the final answer for us that uh, since there were only two queries, so after second query, this is the final answer, which comes out that the parent array will look something like this: 1 1 1 1 3 3 1 1. And out of these options, so 1 1 1 1 3 3 1 1, this is the D option. Can be seen that D option is actually 1 1 1 1 3 3 1 1, which we arrived at. So actually, option D is the correct answer. So yeah, Rahul also wrote that option D. So good job, Rahul. Option D was actually correct. So maybe I'll just write it down also. Hence, option D is the correct answer. And I'll just underline this for proceed. So after this, maybe if this is clear to everyone, if this is not, you can ask me. Just remind you guys. This is clear. Maybe we can move on to the ninth question then. So ninth question is asking us, it's a multiple choice question and it's a straightforward question. Okay. Yeah. So in the ninth question, it asks us that you are using the provided path compression version of the find set operation. So let's say in the disjoint set union, we are using the path compression version. We are actually using path compression. Then the problem is asking us what is actually the purpose of path compression in this context. So when we are using the find set operation, why are we actually using path compression? Like, what's the difference in using path compression and not using path compression? And there are four options given to us. The use is maybe one or maybe more than one can also be correct. We'll just see. So the options are to reduce the number of union operations, to ensure that the DSU, the disjoint set union, is in a balanced state, to make the find set operation faster by reducing the depth of the tree, to ensure that the find set operation always returns the smallest element. Okay, so Rahul is saying that only option C is correct in the chat. So would anyone else like to try this also? So Rasika or Vishal, what do you guys think? Is option C correct or? Okay, so Rasika is saying options A and C are correct. Okay, maybe we can just see what the options say. So note that what does this what does path compression actually do? Just reminding you guys from the lectures, what does path compression do? So path compression is actually used just to reduce the depth of the trees. So what we do in path compression is everyone knows that we just make the parent as the leader itself for all the queries which come along the way in the find set operation. So when we are using path compression, the main idea here is to reduce the depth of the trees so that future find set operations are easier. So future operations are easier to do. That's why we do path compression. And now what? So that's the main idea for path compression. Now maybe we can look at the options individually. So option A says to reduce the number of union operations. So note that Rasika, the query time for each union operation reduces. Like let's say we are given 10 queries of finding like 10 different unions, then maybe the time complexity for doing those unions will reduce because we'll need to because in every union operation also we need to find first the leaders. For that we need to call find set, and if find sets queries reduce, the unions queries also reduce. But the problem is not asking us to, but the option says that reduce the number of union operations. This is not true because the number of union operations are controlled by the queries which we are making. The time taken to do one union operation will reduce definitely, but the number of union operations won't reduce. So that's why option A is incorrect. Uh, do you get the idea, Rasika, what I'm trying to say? Okay, cool. Maybe I can just point this out also. Option A is incorrect, as query time of each union operation may reduce, may reduce, but the number of union operations does not depend on path compression. Right. And similarly, B option is to ensure that DSU is in a balanced state after every union set. So balanced state means that the height is a maximum of log n. But note that again, path compression is not used to make it balanced. Uh, because even if we don't use path compression, we just uh, attach the tree of the lower height to the tree of the higher depth, then also the DSU is in a balanced state. So that's why path compression is also not true for option B. But option C says that to make the find set operation faster by reducing the depth of the tree. So this is actually correct. So this is what we have already seen, that find set operation actually becomes faster and becomes something like order one amortize. And option D is to ensure that find set operation always returns the smallest element. So I think this option does not make any sense in itself. So yeah, it can be seen that this is also incorrect. So similarly, options B and D are also incorrect. Only option C is correct. Yeah. So I hope everyone gets the idea, like why is only option C correct. So yeah. So this was the ninth problem. And now maybe we can move on to the 10th problem, which is I believe the last problem for today. Yeah. So the problem says consider a simple undirected graph G equal to V comma E, and we want to determine if there is a cycle in the graph. And what's a cycle? A cycle is defined as a path in a graph where start and end points of vertices coincide and no edges visited twice. So just to give you an example of what is a cycle in a graph, I believe you guys may already know what a cycle is, but just to give you guys an example. So let's say we are given this graph. This is an undirected graph because none of the edges have a direction. So here actually the vertices 2, 9, and 4 form a cycle of length 3 actually. So I believe if you guys, I believe everyone can see these vertices 2, 9, and 4 are actually forming a cycle. Cycle just means uh, a sequence of vertices, or let's say a cycle is defined as a path where start and end points are coinciding and no edges visited twice. So here we can see that in the path from 2 to 9 to 4 to 2 back, the edges 2, 9, 9, 4, and 4, 2 are used. And yeah, no edges are coinciding, and the start and end point is this vertex 2. So these vertices 2, 9, and 4 are actually forming a cycle. Similarly, 3, 7, and 1 also form a cycle. So I hope everyone gets an idea of what a cycle is in an undirected graph. And note that we say that this cycle is of length 3 because there are 3 vertices involved. So just to grasp that whether you guys have understood the concept of a cycle, uh, does there exist in this graph, does there exist a cycle of length 4? And if there exists such a cycle, can you name that cycle? You can answer in chat also. This is, yeah, just to get an idea whether you understood the concept of a cycle. Okay, so Rahul is saying that 0317 is a cycle of length 4. So 0317. So yeah, Rahul, yeah. you're correct actually that this 0317 is a cycle in this graph, and it can be seen that it also has a length 4 since there are 4 vertices involved. So yeah, so actually this is the cycle of length 4. So yeah, good job, Rahul. So yeah, we can call that this graph has a cycle of length 4. So now coming back to the question. So now we get the idea of what does a cycle actually mean. So now we are trying to come up with an algorithm that involved disjoint set union to solve the problem. And what was the problem? The problem was to determine if there is a cycle in the graph. So we are given a graph and we want to find out whether there exists a cycle in the graph. And for this, we are trying to come up with an algorithm involving disjoint set union. And the algorithm goes something like this. We define the function def find cycle, and the input to this function is the graph G. And we extract the vertices in the second line of the graph. Similarly, we extract the edges of the graph. And then we initialize the parent array. And now we set the parent of I to I initially. And we set a variable is cycle is false. And now by iterating over all edges in E, what we are trying to do is whenever we find two vertices connected by an edge, if find set of u is equal to find set of v, do something one, else do something two, and then we return the value of the variable is cycle. So the problem essentially involves that we are writing some code for finding a cycle, and in this code, we have left some parts out. This do something one and do something two, we don't know. And there are four options for us, and we want to find out the appropriate code to replace do something one and do something two so that the given algorithm finds the cycle correctly. So yeah. So the problem just asks us whether there exists a cycle in the graph or whether does there not exist a cycle. And for doing this, we have written a code using disjoint set union, and we have left some parts of the code out. And now the problem asks us to replace the appropriate parts with the correct answer. So uh, maybe I can zoom out a bit so that you guys can see the options and the code on the same line. So yeah, so we are just trying to find cycle. So I believe you guys can try this yourself. Also think about this for 3-4 minutes. Like, what can we do? Like, what would the logic? So first of all, maybe we can think of what would the logic be for finding a cycle, right? Like, how can we find a cycle using the disjoint set union data structure? And if we get the idea of how to find the cycle using disjoint set union data structure, maybe then we can see how this code works and what may be the correct option to replace this do something one and do something two lines. So just give it a thought, guys. Like give it 3-4 minutes. I'm giving you time, so think about it and yeah, try it yourself first. And you can let me know via chat like what do you think will be the correct answer and why. This is a new problems for you guys. Like it's based on disjoint set union only, but yeah, this problem was also not covered in the lectures, but it's also an interesting problem. And I believe you should look at it and think about it, obviously. And like while trying to think about it, just keep this sort of example in mind. Like you already saw like 294 was a cycle, similarly 3071 was a cycle, similarly 301 is a cycle. So just keeping that in mind these sorts of diagrams, maybe you can think like when is actually a cycle created? And what can we do using disjoint set union data structure to detect that cycle or something like this? So yeah, keeping some sort of diagram in mind may also come in handy for this problem. So just think about it, guys. Yeah, let me know via chat. Till then, I'll mute myself for 2-3 minutes. Okay, so maybe any ideas or any thoughts which come to your mind, maybe you can also type in those also, or any doubts which you have and the direction in which maybe you're thinking, so that maybe we can incrementally come to the correct answer. So any thoughts are welcome, guys. Okay, so Rahul is saying something in chat. So Rahul is saying that an idea can be if a parent of a vertex is equal to vertex, then there is a cycle. Mm. Uh, Rahul, the parent actually, Rahul, I believe you are maybe getting confused between two things. So see, the parent of a vertex and these sorts of things like parent-child relationships are for the disjoint set union data structure. But what we have to find out is we have to find out cycle in the graph. So I believe you are getting a bit confused. So like a parent of a vertex is equal to vertex implies that that vertex is a leader in the disjoint set union data structure. But I don't see how that corresponds to any cycle in the graph, if you get the drift of what I'm saying. Okay, so Jay has written that from source to destination, if there exist two or more paths, then maybe there's a cycle. So yes, Jay. So Jay is thinking along the correct lines, I believe. Maybe it can be refined even a little more. So Jay is saying something like this, that from source to destination, if there exist two or more paths, then we can say that there exists a cycle. And note that here source and destination can be any two vertices. So maybe we can move to the graph again. So we can see that if we consider 2 as a source and 9 as a destination, then there are two paths between, at least two paths between 2 and 9. So we can see that there's a path which directly goes from 2 to 9, and there's a path which goes from 2 to 4 and then 4 to 9. So yeah. So if we keep the source and destination same, and then if there are two types of paths, then we can say that there's a cycle. So note that just building on to what Jay just said, so Jay is on the correct track. I'll just give another idea. Maybe we can even refine Jay's idea to say that uh, for a pair of for a pair of vertices between which edge exists. So Jay is saying, so Jay, you are saying that from source to destination, if there exist two or more paths, right? So from, let's say, if we take source and destination as 3 and 7, there can exist two paths like 3 to 0 and 7, or 3 to 1 and then 7. But what I'm saying is maybe we can uh, change this definition even further to fit our code's example and say that for two vertices which are connected by an edge, there exists an alternate path not containing that edge. So what I'm saying is, so from source to Jay is saying from source to destination, there exist two or more paths. So what I'm saying is consider two vertices which are connected by an edge. Let's say 2 and 9. They are connected by this edge, right? And now what I'm trying to say is what we can also call a similar condition to Jay's condition for existence of a cycle can be for an edge, its two endpoints are connected by another path which does not contain that edge. So like 2 and 9 are connected by an edge, but there exists another path between 2 and 9 which does not contain this edge. So like 2 to 4 and then 4 to 9 is a path between 2 and 9 which does not contain the direct edge. Similarly, for these vertices 3 and 7, there exists an edge 3 to from 3 to 7, but there also exists a path from 7 to 1 to 3, which does not involve this edge. So what I'm trying to say is maybe so we can also say that a cycle exists if there exists, and maybe I should write this down. A cycle exists in G if and only if. So this is the notation for if and only if. I hope you guys know this. Alright, I should write like this. If and only if uh, there exists an edge x comma y in G such that there is a path from x to y not containing the edge x comma y. This is an idea. So first of all, does everyone agree with this statement? So that is this statement clear to everyone? And like, if there's any doubt in this statement, or you're not sure whether this statement is correct or not, or you're not sure what this statement is actually saying, you can ask me via chat. Otherwise, I'll just assume that this statement is clear to everyone. So what I'm saying is a cycle in G exists if and only if we can find an edge x comma y such that there is a path from x to y not containing that edge. And why will this form a cycle? So let's suppose there is a path from x to y not containing the edge x comma y. Let's call that the path P. And so if we add the edge x comma y to that path, then it will become a cycle. That's what I'm saying. Because we go from x to y using the path P, and then we come back to x using the edge y x to y. Something like this. So suppose we want to find out the cycle contain. So suppose we have this edge 3 comma 7, and now we find a path which does not contain this edge 3 comma 7. So this is a path. So what I can actually do is I can go from 3 to 7 using this path. I can take this path 3 to 1 and then 1 to 7. And then I can come back to 3 using the edge, which I had earlier not taken. So that's how I can obtain a cycle. So I hope this is clear to everyone. So that's why this condition corresponds to existence of a cycle. And if this idea is clear, so what we need to actually do is we just need to check if there exists such an edge, such that there is no path from X to Y containing that edge. And now you can actually see that this code is actually trying to do something like this only. So what is it doing? It's in the second line initializing vertices, then edges, and then some parents or something. So let's leave out the 4 and 5 lines. But in 6 line, it's saying first initialize the is cycle variable to false. And now for every edge, what it's doing is it's seeing the vertices connected by the edge. U comma V are the connected vertices connected by the edge. And it's saying that suppose we have not yet added the edge U comma V to the graph. If we have already not added the edge U comma V to the graph, then if U comma V were part of a cycle, then there should still exist a path in the graph G, even if this U comma V edge was not part of the graph. So you guys get the, I hope everyone gets the drift of what I'm trying to say here. So what I'm trying to say is, let's say before inserting this edge U comma V, before handling this edge U comma V, suppose G in G, this U comma V edge was not present. And even if this U comma V edge was not present, if we could have found out a path between U and V, then we would have said that actually there exists an edge U comma V such that there is a path from U to V not containing U comma V. Because we have not yet added the edge U comma V, but we are still obtaining a path from U to V. If we can obtain a path from V, even if we have not added the edge U comma V, then this means that U comma V is such an edge, and so a cycle will exist. So I hope you guys understand the idea here. So this is what this code is doing. So what this is doing is it takes the edge U comma V, and this U comma V edge is already not yet added to the graph. And now this find set function is just trying to see if we already have a path, even if we have not added the edge U comma V, if we still have some path from U to V. And why is this condition find set U equal to find set V equivalent to saying that there exists a path between U and V? Because we had already sort of done this sort of thing in this problem statement also, right? That if U and V belong to the same connected component, like let's say 2 and 4 belong to the same connected component, then there will be a path between 2 to 4. So what I'm saying is suppose this 2 to 4 edge was not present even. And we had considered the vertices 2 and 4. And we are adding the edge 2 to comma 4 now. So you can see even if we have not yet added the edge 2 comma 4, since they 2 and 4 are in the same connected component, there will still be a path between 2 and 4. And now we'll be adding the edge 2 comma 4 back, and this results in a cycle. So the key idea here is something like this only, that initially we don't have, so initially we don't have, let's say, any edge here, and we incrementally add edges and we make them connected in connected components. So 9 and 4 become one connected component. Now 6 and 10 become another connected component. Now 6 and 4 become another connected component. Now 2 and 9 become in the same component. And now when we add this 2 comma 4, you can see that 2 and 4 already belong to the same connected component. So they will actually form a cycle. So when 2 and 4 are added, 2 comma 4 edges added, now this will form a cycle. Earlier it was not, but after adding 2 comma 4, it will form a cycle. And so they are actually, so what this essentially means is that we will obtain a cycle if find set of u was already equal to find set of v. Because find set of u equal to find set of v meant that u and v are in the same connected component. And if they are in the same connected component and we are adding an edge between u and v now, so this results in a cycle. So do something one will actually correspond to something like there is a cycle. So, so what it actually does is it returns true. Maybe we can say that it runs true that there is a cycle, or like, so do something one can do this, that it returns true, or it can also just set the ret is cycle variable to true, and in the end we are finally returning the cycle variable itself. So actually we know that the correct option is one between option B and C only. So do something one will essentially just say, so do something one essentially means that this part will do nothing but just return the, just say that there will exist a cycle. And otherwise, what we have to do is, if we find that the U and V are belonging to different components, then we just proceed as usual, like we did here. That if U and V belong to different components, let's say here, let's say what we did earlier, that 6 and 10, let's say, belong to different components, then we just add the edge and we just make them in the same component. So we just you may take the union of their individual components. So that's what we'll do here. So in the else part, in the do something to part, we'll just be taking the union of the sets of U and V. So that is what the option C is doing. It takes the union set of U and V. So only option C is actually correct. That do something one sets the is cycle variable to true, and yeah, do something two set just gives the union set. So Rahul has also written in chat that option C is the correct answer. So good job, Rahul. This is the idea. Yeah. So yeah, so using the above idea, the idea which we discussed, we keep adding vertices to the connected components till we, and if we arrive at an edge such that the edges of that edge are already in the same connected component, then say that there exists a cycle in G. Maybe I can word it a little bit better. Consider all edges one by one. If we arrive at an edge end such that the endpoints of that edge are already in the connected component, then we say that there exists a cycle in G. Okay. And what we do otherwise, so if we don't arrive at, if the edge is, if the edge is not such that the endpoints are in not the same connected component, then we just merge the components. Endpoints are in different components for an edge. We just merge the two components. So yeah, this one was a bit new question for you guys, and it involved a bit of thinking and some new ideas. But I hope you guys get the gist of it. That the main idea was a cycle exists if and only if there exists an edge, such that there's a path not containing that edge. And now we consider all edges one by one. If we arrive at an edge such that endpoints are in the same connected component, this means that there is already a path in from those endpoints, between those endpoints. So there will exist a cycle. And if the endpoints are in different components, we just have to merge the two components while adding that edge. So because of this, option C is the correct answer. Option C is correct. Okay, so I hope. Okay, so Rasika is asking us, but there will exist only one edge between the two components. So how can it form a cycle? Rashika, so what I'm trying to say is, if the two components are different, then there will exist only one edge. But what we are saying here is that that's what we are saying, that if the endpoints are in different components, then we just merge the two components and we don't get a cycle. But what we are saying is the endpoints are already in the same connected component. If the endpoints are already in the same connected component, then we obtain a cycle. So like say in this example, coming back to this example, so what we see here is before adding the edge 2 comma 9, all these vertices were in the same connected component, right? 2 and 9 were in the same connected component, but there was no cycle. But as soon as we add this 2 comma 9 edge, there becomes a cycle. That's what I'm trying to say. So does it make sense, Rasik? Okay, so okay, you got it. So nice. So I hope everyone understands this correctly. So yeah, I guess guys, this was the last question. I only had 10 questions for today, and I believe it's close to the end time of the meeting. Also, it's 7:58 and meeting it's at 8. So just for parting words, like would anyone like to ask one final doubt or anything? If there is no doubt, maybe we can close the session. Okay. So thanks for the kind words, Rahul. So I also enjoyed this session. So since I believe no one has any doubts, I guess okay. Thank you, Rasika. So since no one has any doubts, I guess we can close the session. So once again, thanks for attending the session, guys. So hopefully we'll see you guys next week also, same timing, Tuesday 6 to 8. So yeah, thanks for attending, guys. Maybe I'll just close the session now and yeah, goodbye.